This is Facility Science Podcast number 3. I am Jason Doolittle, and today I'm talking about VAV, which is short for Variable Air Volume, and specifically I'm talking about multi-zone VAV systems. So VAV is a system design concept that allows for you to use a single air conditioning plant, so a single source of conditioned air to cool. I'm going to talk about cooling just by default, just to make it simpler so I don't have to keep going back and forth between cooling and heating. So to cool or to condition multiple independent spaces, which each have their own potentially different heating and cooling and airflow requirements. So one source of air, multiple zones or areas with their different requirements for that from that source of air. So, for example, we can describe a hypothetical building with 4 cooling zones, and each of these zones will have its own thermostat, but then we only have the one source of air. So our 4 zones in this hypothetical building might be, you have a hallway with a few offices in it, and so these would have a relatively constant demand for cooling during business hours. The second area would be, say, an employee break area, which would have a high demand for cooling during the common break times, but a low demand during the other times. Third area would be maybe a storage area, which would have a relatively constant but low demand most of the time. And then our fourth area would be, say, the production area in your business, which would have a high demand for cooling during each production shift. All right, so the basic idea of how a system like this would work is you have your air handler and cooling and heating apparatuses, and that system supplies air that is a constant temperature in general, although that temperature can be manipulated with the control system. But so it supplies air that is a constant temperature into the main supply duct, and then you have what are called VAV boxes, sometimes called VAV terminal units. These are units with an air valve inside that connect to the main duct and control access to the space that they're serving, and that the thermostat would be attached to them. And these boxes, they have a valve in them that opens and closes depending on the demand for conditioned air in their space. And then the air handling system, the air handler, would adjust the flow of air into the main supply duct to attempt to keep the pressure or airflow in the main supply duct at some constant. So if you think about it, when more VAV boxes or terminal units are more open, then the supply of air will need to be a higher volume of air into the main supply duct to maintain the airflow or the proper pressure. And when the VAV boxes are mostly closed, the fan will need to move a lower volume of air into the main supply duct to maintain the same airflow or pressure. So now let's go into more detail into the parts of the system. So the first thing, you have your heating and cooling system. And since we're going to be supplying a variable amount of conditioned air, a heating and cooling system in this type of system is probably multi-stages, because you're going to have those differences. So you might, when you have a low demand for say cooled air, you might only run one cooling stage in your multi-stage cooling system. And when you have a really high demand, as demand goes up, you would then stage in the stages and have more and more coils or compressors running to cool a larger volume of air. And then heating in a system like this can be done at the main supply, and I'll talk about that a little more later. But very often the heating is done remotely in the zone. And then another thing that's true about a system like this is that this main supply heating cooling system here probably doesn't even need to know about the zones. It just controls the temperature, so it puts whatever is the set temperature of air into the supply duct, and that's all it needs to do. All right, so next you have the actual air handler itself, so the part that actually is going to move the air over the coils and into the main supply duct. And so this has a fan to pull air from the return duct or from outside or wherever it's getting air, and pushes it into the main supply duct, probably across cooling stages. And then it also needs some mechanism to control how much air it's pushing into the main supply duct. And the air demand from the air handler's point of view is determined by measuring the pressure in the supply duct, usually the pressure, but sometimes the airflow. And some examples of mechanisms that the air handler could use to vary the amount of air that it's pushing into the duct in order to control the pressure are, for example, recirculation or inlet dampers to restrict the amount of airflow. So it just kind of closes a little door so that less air goes through, or manipulate some dampers so that instead of the air going into the supply duct, it just goes loops around back to the input of the fan. Another example would be a variable pitch fan. So the blades on the impeller actually move. So they change the pitch so that with each revolution of a constant speed fan, more or less air can be moved by just changing the angle of the blades on the impeller. And various methods of speed control. So a common method for speed control in a modern system would be a variable frequency drive. So you can actually run an AC induction motor that would be turning the fan at any speed you like by using an electronic variable frequency drive. And there's also other ways to do this with actual variable speed motors. So you might have multiple discrete speed or gear ratios or something like that. And there are other methods as well to allow the air handler to control how much air it's pushing into the supply duct. And like the heating and cooling systems, the air handler, again, doesn't necessarily need to know anything about there being zones. All it needs to know is the duct pressure, which we call static pressure. Usually when you hear your HVAC contractor or mechanic talking about the pressure in the duct in a VAV system, they're going to be talking about the static pressure in the duct. All right, the next piece of the system is the main supply duct. And so the main supply duct carries air from the air handler and it branches toward each zone. And the branch to each zone ends in a terminal unit, like I talked about before, a VAV box, usually called. And the VAV box or the terminal unit separates the zone ductwork from the main supply duct. And usually the VAV box will have a temperature sensor connected to it and pressure or airflow sensors so that it can monitor what's going through it. And the temperature sensor from the space, the thermostat in the space, is usually connected also to the VAV box. All right, so now we have the terminal unit itself we'll talk about. And so you'll have one terminal unit for each zone to separate the zone ductwork from the main supply duct. And the terminal unit, the VAV box, has inside of it a motorized damper, so an air valve basically, that it can open and close to control the amount of air that's allowed to pass through from the main supply duct to the zone ductwork. And then a temperature sensor in the space that allows for control of the damper. So in the cooling scenario, as the space gets warmer, the damper opens more to allow more cool air into the space. And as the space cools back down, the damper can gradually close to restrict airflow, to let less of the cool air into the space. And this continuous but variable flow of air allows for a more constant space temperature than what would you normally maybe have in your home, which is a constant volume system where the air supply is either on or it's off, right? So it's a slightly finer control of this temperature in the space by opening and closing this valve and always allowing air to flow through the space, but controlling how much of it actually goes in. And then after the VAV box, you have the zone ductwork. So this branches through the zone space and ends in the supply grills that are actually in the space that the cold air actually comes out of and goes into the space. And then finally, the last piece of this puzzle here is some method to have return air go back to the air handler or to exhaust outside. Right now, an important concept in VAV systems is the concept of reheat. So since we have a constant supply of, in our case, cool air going into the space, often a zone will need a minimum flow of air through the VAV box to make up for some ventilation air that is exhausted out of the building or something like that. So you'll always want some air coming through the VAV box. But when the air in the space has reached the actual desired temperature, we're still going to have cold air flowing into the space because we need that makeup air for the ventilation. So the space is going to get too cold. And so to prevent overcooling, some of these VAV terminal units will have a reheat coil. So this could be any kind of heating mechanism depending on what's designed into the system, hot water or electric heat or whatever it is. And that allows the excess cool air to be reheated so we don't overcool the space because we only have this one temperature of air to come in to supply the makeup air for the ventilation. All right, so Now let's talk about methods of supplying heating with a VAV. In I don't know, I want to say most cases, but I think in most cases, the main air supply in a VAV system is going to be cool air. So we're cooling by default. So how do we provide heat in a system like this? Sometimes, depending on the climate in the area, you might have central heat. So you'll switch your primary air supply from cool to heat. And this is often done in a lot of buildings for, the morning warm up of a building that has been unoccupied during the night. And so we need to warm it up so that it can be at a comfortable temperature for people. But then once the business gets going in the building, we're going to be cooling the spaces. And usually a system with central heat will do that. But, obviously could be designed in such a way that when most of the demand in the building is for heat, we'll just switch off the cooling and turn on the heating, central heat. So all the heat comes from the central air handling equipment. Okay, now in the central heat scenario, also, I remember I talked about reheat just a minute ago here. If you have a majority of zones calling for heating, but maybe one needs some cooling, or the hot air is overheating the space, just like in the reheat situation. Rarely, but sometimes you might have a system designed with recool, so you'll have auxiliary cooling to recool the warm air at the zone, so in the VAV box or in the zone otherwise. That's not as common as the reheat scenario, but it's possible if that makes sense in the particular climate and use of the building. All right, so the second method that is used to supply heating with VAV is terminal heat. So this is when the primary supply air is always cool. Heating would be done by either remote heating equipment in the space, so radiators or some other kind of space heater. Reheat coils in the VAV boxes. So this is the same mechanism that would be used in the reheat situation. That heating coil in the VAV box can provide the heat for the space. And in a place where you have a relatively warm climate where you're pretty much always cooling, the reheat coil in the VAV box is potentially the only source of heat in the building at all, because it's not used as often. But in a cold part of the year, you'll just be heating with those VAV box reheat coils. And then you could also have, in the terminal heat situation, VAV boxes that will mix the return air into the cold supply air using various fans and dampers. And this would save energy on reheat by basically using some of the heat that's being exhausted out of the space from the processes that are going on in the space to reheat or to warm up the supply air, the cold supply air. And a benefit of doing this isn't really that common, but a benefit of doing this is since you're mixing in the warm air, you can potentially maintain a more constant airflow into the zone, because you don't have to close the VAV box so far down in order to prevent overcooling of the space. A third method of supplying heat in a VAV type system that I want to talk about is a dual duct system. So in this kind of system, you'll have two primary air supplies, so one hot and one cold. And then the VAV boxes, the terminal units, can mix air from the two sources to achieve the desired temperature in the space. And this can be more expensive to operate because you're basically heating and cooling air all the time. But the upside of something like this is that it will allow you to very precisely control the temperature the air temperature that's going into each space, which will give you more fine-tuned control over the space temperature. All right, now I want to talk about some issues to look for if you are running a building that uses a VAV system. These are going to be just a few issues that I've actually encountered in the past, not a comprehensive list, and in no particular order. The first one is clogged reheat coils. If you think about the VAV box with a reheat coil in it, what that basically is you have a box with the valve, the damper that opens and closes, and then you have a coil that's basically potentially an obstruction for airflow. And if you get over time enough stuff in the ductwork, you can clog that reheat coil so no air can get through. Some VAV boxes, and I've seen this, have no provision to access the interior of the box and clean the coil. And so you might have a situation where you're running the system all the time and everything looks fine, but no air is actually getting through the VAV box into the space. The valve is opening and closing just fine and everything looks like it's working, but air is not getting through. And that's because your reheat coil has been clogged up by, dust, lint, whatever it is. And so the way to check this is you can check all your VAV boxes in your control system, hopefully you have this capability for the proper airflow at the given valve position. So, I mean, obviously, if you see a situation where your air valve in the VAV box is at 100% open, but your airflow through the box, and a lot of them will have this information available because they have an airflow sensor in the box, is at 0 CFM, so you have no air through, but the valve's all the way open. Well, then you have a problem. You might have a clogged reheat coil, and you got to get in there and clean that out. So that's a situation that I've seen. Another common situation, common problem in a VAV system is excessive reheat. So this is the situation where you'll notice, hey, the boiler is running, but it's summertime. Why is the boiler running? And this can very silently waste a lot of energy. And I say silently because everyone will be comfortable and no alarms will be sounding. So it'll look like the system is working just fine, but it's not working as efficiently as it could be. It's doing too much heat. This can be hard to diagnose. So some ideas around this are that the reheat should only be active when the air damper is at its minimum position, right? Because if the only reason you want to activate the reheat in a general cooling situation is because you have a zone that needs airflow, and the damper is closed as much as it can to allow the airflow necessary. But now we're going to overcool the space, so we turn on the reheat to make sure we don't overcool the space. So if the damper can close more, then the reheat shouldn't be on. So if you have, in this situation, a wide open box with reheat active, so it's heating, that indicates some kind of a malfunction, right? Another thing that can cause this excessive reheat is missized boxes or inappropriate minimum airflows. So you might have a box that's too large for a space, so it's just can't put out a small enough amount of air to make that space comfortable, and so you have to reheat because of that reason. Or maybe you have the minimum on that box set too low. Set too high. So you're putting more cold air than necessary, and so the reheat has to come on. And maybe if you adjusted that so you're putting less cold air, so your minimum airflow is less, you wouldn't have to do the reheat. And then another maybe reason for this would be that you don't have the optimum control system parameters. So, for example, the supply air temperature set point, the heating deadband, the static pressure set point, all these being not set at the proper setting can allow for excessive reheat. And so let me give you an example of what I mean by this. So imagine you have a situation where you're putting a certain cold air temperature into the main supply duct, and the space with the least need for cooling has its VAV box closed to the minimum it could possibly be, so now it has to reheat. But if you think about what about the space with the highest demand for cooled air? If that one isn't all the way open, so it's closed partially, say it's 80%, 75% closed, or 75% open, then in order to maintain the temperature in that space, it only needs to be 75% open. Then possibly what you could do is increase your air temperature so that space with the highest demand can have its VAV box all the way open, so you're maximizing the capacity of that box, which would mean that the spaces with less requirements for cold air might not have to reheat as much because the air coming into those spaces is now warmer. So their boxes can be satisfied with their minimum air, or maybe those boxes can even be opened up a little bit more. And that way you can save heat. And getting this right depends on really knowing what the load is in each space, how the demand varies, and so you really kind of need a competent engineer to design this kind of thing to get it just right. And then the third issue that I want to talk about to look for in a VAV system is changes in space occupancy, because a change in occupancy from the original design can unbalance a system like this. So during the design phase, the VAV boxes are chosen based on the expected heat load. So the expected amount of heat that's going to be generated from the activity that's happening in that space. So if, for example, a storage room, so a room where the air conditioning system was designed and the VAV box was installed with the assumption that this is a room used for storage, so a low general demand for cooling. If you turn that room into a machine shop, the existing terminal unit will not be able to provide enough cold air to the space. And one thing this could cause is that, well, that space will never ever be cool enough because your VAV box is too small. But another thing this could cause is it could cause a situation where you're overcooling the rest of the building, which means you're then excessively reheating the rest of the building as the system tries to do everything it can to satisfy this broken zone. And sort of a naive approach, if you have this situation, would be, oh, this space isn't getting cold enough. Let me turn down the supply air temperature set point, and everything will seem to work because, okay, now we've gotten this space to the temperature it needs, and all the other spaces are the temperatures they need to be, but really they're being overcooled, and now you're wasting a bunch of energy with excess reheat. And again, this can be fixed by modifying the system to reflect the new occupancy of that space. So in this case, the most obvious thing might be to replace the VAV box with a larger one. But again, it can be tricky to do this right. So you'd want a competent engineer to figure out what's the right thing to do in your space. All right, so that's what I have to say about VAV. I have some notes with some links to some more information if you're interested on the website. That's facilityscience.com/podcast. And this is number 3. If you have questions, comments, suggestions on this topic or any other, you can reach me at podcast@facilityscience.com. And I hope this was helpful for you. So thanks for listening.